Hello, it's Keith here, and this is lesson 3 of my Risc-V Assembly Programming Tutorials, and this is actually the last of the Risc-V series. It's a pretty short series, really. Today we're going to be looking at basically all the commands we haven't covered so far, which is primarily logical operations. This is ANDs, ORs, XORs, that kind of thing, bit shifting, and we're also going to be looking at some other strange commands with regards to conditions that Risc-V has that are quite alien to me, quite new. So we're going to have a go at those. We're going to go over straight to the source code. We're going to take a look. Okay. So first of all, we're going to start with logical operations. These are bitwise operations which have a condition, and the two parameters will be combined together in some way. We'll look at all of them. So let's fire up the example and let's see what happens. Okay, let's get my example onto the screen here. That'll be a good start. Okay, so we've got our examples here, and what we've done first is we've loaded some test data in here. You can see we've loaded A0 and A1 with just a sequence of numbers 1 to 8, and then we've loaded A2 with a mask here. And you can see here we've loaded the top 16 bits with all Fs here, and we're going to use that as a mask with the other ones with these logical operations. Now the first one we've used is XOR, exclusive OR. Now what this will do is it will take the A2 parameter and it will XOR, exclusively OR it with the other parameter A0 in this case, and we've got XOR I, which is XOR with an immediate, and we're XORing A1 with FF here. And what this effectively means is where the bit in the parameter is a 1, then the bit is flipped in the other parameter. Where it's a 0, it's left unchanged, and we can see that just here. So you can see here we've got our starting parameter of 1, 2, 3, 4, 5, 6, 7, 8, and we've exclusive ordered that with our quadruple F, quadruple 0. And what that's done is it has flipped the top 4 nibbles, E1, 2, 3, 4 has become EDCB, whereas 5, 6, 7, 8 have been left unchanged, and that's because those bytes were all bit zeros there. So that's what has happened. Now you can see the second example, it was 1, 2, 3, 4, 5, 6, 7, 8, and that was exclusive ORed with the immediate value FF here, and so that has had the effect of flipping the bottom 2 nibbles from 7.8 to 8.7. Now, I'm using FF here as a sort of clean example, but we could just set a single bit here. If I change this to 0.2, that's effectively just setting bit 1 to a 1 there. And you can see here, if we just look here, now you can see that that 8 has become an A. And if you look at the bits, you would see that only bit 1 has flipped there and the rest have been unchanged. And that's what the exclusive OR does. Now, the next one we're going to be looking at is AND, and you can see here we've taken those parameters again and we've done an AND. And so in this case we've basically taken the previous parameter, which you can see was EDCB5678, and this time we've ANDed it with, again, that mask of the top 16 bits as 1 and the bottom 16 bits as 0. And will be resulting in a 1 where both of the parameters have a bit 1, and will result in a 0 when either of the parameters have a 0. An AND operation, I mean, it's quite logical if you think about it. And so what that effectively does is that where the bits are 1, the parameters bits are retained. Where the bits are 0, the parameters bits are lost. So EDCB has been retained because those bits were 1. But the bottom bits have all been lost and they've been converted to 0 because the bits were 0. And where we worked with the immediate, you can see all of the top bits have been removed and only the 7A has retained because we ANDed it with an FF there, which is effectively 255 8-bit ones there. That's AND-I, ANDing immediate there. And the final one is going to be OR, and OR-I. And this is the opposite of AND. And what this basically says is where the bits in either parameter are 1, the result is going to be 1. Where both parameters are 0, the result is going to be 0. And this has the effect of setting the bits to 1 where the bits in the parameter are 1. And so this time we're using some different parameters. This time we're loading A2 with the top byte as CD here. And we're using CD here as well. And what this is going to effectively do is it's going to almost add that value to the parameters here. So you can see here we had before EDCB and then 40 nibbles there, but now the bottom byte has been set to CD because of that OR, and in this case the top byte was ORed in with CD, and so that has been set as well. But it's not to say that we've added CD in any way. It's set those nibbles and bytes to that value. And so if we change this and we change these bytes to FFFF here, and we ran this again, it's not an add command, it's setting those bytes based on that OR parameter. So you can see here now we've got that parameter as FFFF here, and then the top bits have now been set to all ones there, because as I say, it's if either parameter is 1, has a bit 1, then the result will have a bit 1 in that position, whereas if both parameters have a bit 0, the result will have a bit 0. I mean, it's common. I mean, I suspect you probably know these. I'm maybe explaining things you're already aware of, but I do try and cover these from as low level as possible, so maybe you've not come across these before, but that's how they work. Now, the next one is quite a nice command. I quite like this one. Some other systems don't have it, but this is basically called load upper immediate, and this is kind of one that's probably working in the background for us automatically when we're loading values in. Like when we're loading immediate values up here, we're loading very large values here, and these actually in a lot of cases can't be loaded in a single command, and so our assembler is converting these to 2 commands, one loading the low part and one loading the high part, and it's load up immediate that does the job here. And what this basically does is it loads the top area of each of the registers with a value. So you can see here we're loading some values, and these are actually loaded in to the high parts of the registers, and as I say, these will actually be used as in those pseudo operations to set the registers for us. So what we've done here is we've used a variety of load upper immediate commands here, and you can see them here, and you can see here we've set the top part of each of these. This one we just set a byte worth of ones here, so that's just a double F there. And then this one we set 4 nibbles, so we've got quadruple F there, and that one we set the entire upper part, and so we've got 5 Fs there. As I say, this is probably one you're not going to need to use directly unless you're using an assembler that can't do that pseudo operation and work out when to use it for you, but it's being used within that load immediate pseudo op to fill in the top part that can't be loaded in entirely in a single command. Now, the final commands we're going to look at are going to be the not command and the negative command, and these are sort of similar. The not command is effectively where we flip all of the bits in a register, and this is effectively the equivalent of exclusive ORing it with a parameter where all the bits are 1. Negative is sort of similar. This converts a positive number to a negative, but I say it's similar because the logical operation for converting a positive number to a negative number is we flip all the bits and we add 1. So they kind of are similar in that way. And you can see those. We've got our values over here. We've loaded A2 with 1, 2, 3, 4, and then we've effectively flipped all of the bits and we've stored the result in A0. And you can see we've got FFFF, EDCB, that's all the bits flipped. And then the negative command, as I say, effectively flips all the bits and adds 1. So you can see we had CB and then A1 equals CC, the result of that negative command. So that's what that does. And of course, that's going to be something we're going to need to convert positive to negative and vice versa. Very handy there. What we're going to look at next is bit shifting commands. Now, bit shifting commands can be quite handy, especially in 8-bit and 16 bits, because if we shift the bits to the right, it has the effect of halving a number, and if we shift bits to the left, it has the effect of doubling a number. And these are very fast. These are much faster than even if we have one. Usually a multiply command, at least in 16-bit systems, this is much faster to do bit shifting than to do multiplication, and on 8-bit systems we rarely have multiplication. Now, the important thing to understand with this is if we do these bit shifts, we need to bear in mind if we're using signed or unsigned numbers, because a negative number, if we just shift all the bits and add a 0 at the top bit, we would effectively flip the sign of a negative number. So if our number is potentially signed, we need to make sure we're using the right commands to cope with that. Okay, we're going to try out these bit shifting commands then, and we'll have a look at them. So what we're doing here is we are loading a loop counter here. We've got our loop counter 4 here. We're loading a test value here into A0. You can see this nice long number there, and we're going to see the bits shift around in there. What we're going to do first is we're going to do a shift logical left here. We're going to shift A1 by the bits in A3, and that is going to be initially just 1 bit here. We're shifting 1 bit to start with. So shift left logical will shift the bits to the left, and shift right logical SRL will shift to the right. Now we're shifting by a register, but we can also shift by an immediate value with SLLI here. We can shift by an immediate value. We're shifting by 1 there, and we can try that out as well if we want. So we've got our starting value of 2001 here. And what we're effectively doing is we are repeatedly shifting this here to the left. So you can see that that 8 000201, the 8 has actually got pushed out there, and then when we shift the 2001, that becomes a 4002, effectively doubling the number. Now you can see that top 8 has got lost there, but when we double that 4002, shifting to the left again, that becomes 80004, and then 10008, and so on. As I say, we're seeing it in nibbles here, and maybe it's not quite so clear, but if you look at it in bits, you'll see effectively the bits are shifting by the amount specified, in this case 1 bit each time. And then here we're shifting to the right, so you can see 800201 becomes 4001 000. That 1 has got lost that time, and then that becomes 2 quadruple 0800, and that's the effect of the shifting to the right there. So that was the effect of shifting by a register, but this time we're going to shift by an immediate, and this time we're going to shift by 4 bits this time. So we're going to shift by 4 bits, effectively 1 nibble. And I think this will make it clearer, if you didn't understand what was happening before, what's actually going on here. So you can see now that we're effectively moving by 1 hexadecimal digit each time. And you can see here, those digits are moving to the left each time. And you can see here they're moving to the right. Now the problem is that that A2 with that 8, that effectively the top bit is a 1 there, that has changed sign, because that first value was a negative number, but the second value is a small positive number, and it's getting smaller each time, and it's become positive, and we want it to stay negative if we wanted to effectively halve a signed number. And that's the problem with the logical ones. The logical ones, the logical term refers to working with unsigned numbers. We use the arithmetic shifts to shift by signed numbers, and we actually have examples of those down here. Now, interestingly, we have a shift right arithmetic, and this will effectively retain the sign. And the way you do that is every time you shift to the right, any new bits, instead of creating them as a 0, you create them with whatever the top bit used to be. So your top bit, bit 31, will be any new bits that are pushed in, however many bits you're adding. Now, you don't need a shift left arithmetic, because you always want to add zeros when you're shifting to the left. So we've got a shift right arithmetic, but you can use shift left logical for effectively doubling a negative number, provided you're not exceeding the range that the negative number can be stored in a 32-bit number. And we're going to see that over here. So I've got our value here, and we are effectively shifting right in an arithmetic here. And you can see here that as new bits are being added, they are retaining, they're always FF here, and that's because we're retaining that sign as we're shifting to the right here. And you can see as well here, we're shifting to the right, but again, any bits that are added are always going to be a bit 1, because the top original bit was a bit 1. Now, if I change our test value here, if I change this to a 4 here, the top bit is now a bit 0. This is now a positive number, not a negative one. And if I run our example again, well, you can see now all these new values being added, the new bits are now bit 0s. So it's not that the top bits being added are bit 1s, it's that the top bits being added are whatever the old top bit was, and that's how we retain the sign as we're shifting to the right, effectively halving the values in those registers. That's what it's all about. Okay, so that's our bit shifting operations, and the last one we're going to look at is these. To me, they seem quite strange, these set commands. Now, I'm sure these are something that are incredibly useful. I've just got to be honest, I've never had them before. They've not been any of the system I've really worked with, so I'm not immediately clear where I would particularly want to use them. But basically, what they do is they have a condition, and then they set a register to either 1 or 0, depending on that, if that condition was true. So we've got a few of them, and I think some of these are being done by sudo ops. So we've got a set if less than unsigned, a set if greater than unsigned, a set if less than, and a set if greater than. And these are basically taking 2 parameters and a destination, and what they're saying is if A1 is less than A2, then set A0 to 1, otherwise set it to 0. So these are basically setting the first parameter, the one on the left, in this case A0, depending on the relationship of the other 2. And we've got, as I say, we've got set less than unsigned, set greater than unsigned, set less than, and set greater than, which are of course the signed versions. We do have versions that work with immediate numbers as well. So these are a little bit strange to me, but basically, as you can say, we're doing set less than unsigned here, and we're setting A0 here. Now 14 in hexadecimal is greater than F in hexadecimal. So A0 has been set to 0 here, but then the second time we're doing a set if greater than, and of course it is greater than, so A0 has been set to 1 here. We're then continuing and we are doing our signed versions, and this time we're using a negative number here, and so this time we're doing if A is less than that very high unsigned number, that very low signed number. So again, it's been set to 0, and here of course it's been set to 1 because that number is in fact higher than that negative number there. As I say, very strange commands there, but now the important thing of course to notice is if we set A0 to 1 to start with here, and then we run these commands again, it is being set to 0 if the condition isn't true. So it's not that it's being left unchanged, it is being set to 0. Anyway, that's the last example we're going to be looking at today, and in fact at this stage in these Risc-V tutorials. Now I'm hoping someday I'll be able to come back with some kind of emulator or something, some kind of system that we can actually program some assembly on, because at the moment we've just been using a simulator, which I found Risc-V very interesting, but I would like to program some kind of real system, albeit through emulators. But I've personally enjoyed Risc-V. It's very similar to MIPS, I believe. So you know, it's not that it's particularly unusual, but for someone who has only previously come across 68000 and ARM and even PDP-11 and things, it was a very different way of working with things, and I personally found it very interesting, and I hope you've enjoyed it too. If somehow you've come across this as your first episode, of course you can go to my website, download the source code, download the build scripts, and I've got the pre-configured testing environment to the simulator that we've been running on, so you can go ahead and grab all of that. Anyway, I hope you've enjoyed this today. Thanks for watching. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers, so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.